Okay. Well, welcome everybody. Thank you for coming to today's seminar. It's a pleasure to welcome today Dr. Sandra Kuebler from Indiana University. Dr. Kuebler is an associate professor in computational linguistics in the Department of Linguistics at IU, where she's been there since 2006. She completed her PhD at the University of Tübingen in Germany. Her research interests are on integration of linguistic knowledge into machine learning and in computational linguistics. She's an expert in parsing morphologically rich languages, and she also does work on co-references, resolution, and sentiment analysis. And I know many of you are interested in this topic. It's a great pleasure to have you here to talk to us about inferring underlying opinions from text. And computational linguists are special creatures because they're neither computer scientists nor linguists.
And they have 7 legs.
Yeah. Somewhere in between, but I think they do extremely interesting work, and it's a pleasure to have you. Thank you for coming.
Thank you for having me. Thanks for coming, everybody, because I'm not sure if I'm going to disappoint you. I titled this talk From Text to Underlying Opinions. And the disclaimer at the very beginning is we're not at the underlying opinions yet. We're trying to get there, and we have different ways of doing that, but we haven't really managed that yet. So this is basically a project that we're running at the moment. The project, I always have to look up the title, I can never remember that, is on opinion dynamics in social networks, latent attitudes, and observed behavior. This is funded by the Office of Naval Research in the SAID program. Don't ask me what SAID is short for. I think it's about asymmetric something. Challenges. It's their IED program. So what we're trying to find is a principled, mathematically rigorous approach to modeling, estimating, and tracking opinions in social networks. And if you're expecting a lot of math today, sorry, I have to disappoint you, because this is the part that the people at the University of Miami are doing. I'm the NLP person, so I'm doing the natural language processing part. And that means that part of this is fusing information, fusing soft information. I had to learn what that means, human output, speech, language. And that means we have to convert the language into something that is meaningful for the fusion algorithms, which for us means translating it into some kind of meaning representation in terms of first-order logic. So this is the project overview. Here are our social networks that somehow come in because we have to have some kind of data source where we get the information from. And if you've ever worked on a project with ONR, they're nice about funding you, but they're not very nice in terms of giving you data. So you're always on the lookout for data that you can use, and social networks are kind of interesting things to work on. So what we actually want to do is we have observed behavior. This is basically the language that people produce when they talk to you, when they tweet, when they have chat fora, whatever. And they make something like, I probably won't get my child vaccinated. Underlying that could be a lot of different beliefs. One of them is, sorry, this is not very visible, that the vaccination probably leads to autism in children. So under the statement that a person makes that I won't have my children vaccinated, there could be something underlying it saying that I think if I vaccinate my children, they may end up autistic, or they may end up sterile. That's the other assumption that you could have. So we want to get from this observed layer to latent attitudes, so attitudes that are underlying that and that cannot be observed directly. And that means we have an opinion model where we're talking about where are the opinions and what do they mean. And we have a cognitive model. So we have a cognitive psychologist actually involved in the program. So we're trying to make sure that whatever models we come up with actually kind of make sense in terms of how humans do that. Here's my collaborators. Kamal and Manohar are at the University of Miami, and they're fusion specialists. They're working on the mathematically rigorous part. Deborah Lieberman is the cognitive psychologist. Nasrul Shaikh is responsible for working with the social network stuff. At IU, my students who are working on the project currently are Chan Liu and Eric Borkum. Chan is responsible for the sentiment analysis part. Eric is mostly responsible at the moment for simplifying sentences, and we'll see how that plays into the whole thing later on. Other collaborators that we had are Ning Yu, who is now working for a company in DC, miss you, and Levi King, who's still working on parsing stuff, and we'll see some of his work later on, if we ever get to that. So, next question. What exactly are we investigating at IU? One of the questions that we have is, you have this text, and not all text has opinions. So how do we find the opinions in text? And more specifically, how do we find where is there a positive and where is there a negative sentiment, and potentially also how strong is the sentiment? So you can be mildly happy with something, you can be totally enthusiastic, and that it's important to know what kind of level of opinion you have in there. We also want to know, we worked with several sentiment analysis tasks, and we had to get our own data sets. It turns out that all of them are skewed, heavily skewed. So you have, in our cases, you have a lot of positive reviews. If people like something, they write reviews. We didn't have a lot of negative reviews. So people who hated something just didn't leave any reviews. And I guess if you're indifferent, that's kind of clear. You don't spend the energy on writing something up. So we wanted to know, how do we determine the best features that allow us to classify reviews into how good the things are that they're rating. The next question is a really tough one. How do we extract meaning from text? So this is going into the direction, how do we get meaning and represent it as first-order logic statements? And for that, unfortunately, we first need parsers. And this is one of the areas where I hope I know a lot about. So we're trying to figure out how to improve the parsing before we can do anything else. We also have to simplify the sentences because converting standard sentences from reports or whatever, or from social networks, into meaning is really tough. So we want to simplify them first before we can actually translate them. So let's start with the sentiment analysis thing and see if we can actually get to the parser or not. I don't necessarily have to talk about the parsing stuff. I thought the sentiment would be more interesting for you guys here. So sentiment analysis is not new. It's been around for a long time now. Our focus, I think, is that we assume that if we have user ratings, and we have different areas in which we do that, if we have user ratings, and that can be used as a first approximation of underlying opinions. So again, we have the observed layer, which are the reviews, and then we have the ratings, and sometimes the ratings don't really mesh with the reviews. So it's definitely something getting closer to underlying opinions. We have two scenarios. We have user ratings for recipes. So we're trying, from one webpage, epicurious.com, we try to look at the reviews of recipes and then predict how much the users like this recipe. The other one is from YouTube. We actually had funding from YouTube, from Google at some point. They wanted to find out, if you look at two videos, which one is the funnier one. And we were supposed to do that just by looking at the reviews of the videos. Well, funny is kind of easy. If you look for funny and ha ha ha, you're halfway there. Cute is even easier. You just look at how often cute occurs, and that gives you a pretty good distribution of how well people like the video. But again, we have heavy skewing, so it's easier to predict the majority class, which is a fairly high rating, but it's much harder to get the ones right that they didn't like. The questions here were, how do we deal with extreme skewing in data, and can feature selection actually help? So for those of you who have done some kind of machine learning classification, my classifier has a tendency to always go for the majority class. And it's really hard to get past that and to get the minority classes right. And sometimes you're more interested in the minority classes. If somebody has a very radical opinion about a recipe in this case, you may want to know that, because maybe something is wrong with your recipe, or maybe something is wrong with the person, who knows. So we're trying to find out if, oops, that was unexpected. We're trying to find out if feature selection is actually a way of dealing with that. And then if you go back to the recipe question, we have a lot of different reviews, and all of the reviews are rated. And the question is, how do we get to the overall rating? Does it make more sense to first classify the individual reviews and then aggregate over them, or do we go straight and take basically all the reviews together as one big document and classify that into a rating? Both of them have disadvantages and advantages. We'll talk about those. And then the last question is, okay, we have this standard approach bag of words. We look at all the different words that occur in the reviews and maybe select some of those that hopefully are good discriminators between positive and negative. Can we do better? Can we actually sit down as linguists and come up with features that we actually think are meaningful and do those work better? Okay, what did we find? So this is Epicurious. We have a recipe, and we have information about the ingredients. We have information about the preparation, and here we have the reviews. And almost every review, a lot of reviews have their individual ratings, which are then aggregated in the overall rating for the recipe. However, the problem is a little more difficult, because you can write a review without leaving a rating, but you can also leave a rating without writing a review. And in a lot of cases, you have a lot more ratings than reviews. So people find it easier to click on 4 forks or 3 forks than sit down and actually type in a couple of sentences. So this does not, it's not the average of those ratings, which makes the thing a little harder. I have some review examples.
I'm sorry, do you use only one or the other, or do you use them jointly? What happens when you only have one, not the other?
We used them, we tried all the different settings, and I'll show you the results. Yeah.
Do you know who, the identity of who made each review? So for example, if you have like, I see.
We could get at something like this from at YouTube, because now their YouTube comments have to be linked to Google Plus accounts, I think, which may give us some information. But from experience, we also know that in such accounts, people tend to not always be very truthful. So I have a friend who has a Skype account, and my friend is female, and she's about my age. And her Skype account says she's from Afghanistan, she's male, and she's about 20 years older than she actually is. And there's good reasons for that, because as women, you tend to get contacted by a lot of different people you don't even know. So it's hard to get at the identity behind people. Okay. A couple of examples. It emerges from the oven as a crunchy, gooey, caramelized delight. What do you think? Is that a good or bad review? That should be fairly easy, right? And I mean, if I read crunchy, gooey, caramelized delight, maybe not here caramelized, but delight and gooey and the crunchy actually have positive connotations. So I have actually positive words in here. And the next one, way, and I mean way too much salt. Again, it's fairly easy to see that this is negative, right? But actually, that's easy for me. There aren't really any negative words in there. So there's nothing like disgusting or awful or bad or not even not in there. this is a lot more indirect. This is my favorite sentence. My curiosity was satisfied, but not in a good way. Yeah.
Isn't the phrase too much negative?
The phrase, if you ask a linguist, they could probably come up with a couple of contexts where it's actually positive. But yes, too much together has some kind of negative connotation. But you have to be a little careful there. Here we have satisfied and good, which are actually positive words, but then we have but and not in there, which are negative words. So we get it, if we just look at individual words, we get an actually mixed message. Next one, my husband, who said he despises fruitcake, said this cake is out of this world. If I just look at individual words, I find despises, which is negative, and out of this world, which should be the positive part. This is a collocation, so I have to know the meaning of the collocation in order to get to the positive meaning. So this is a really tough one. Skip the next ones. Oh, this is another good one. It is hard to give this rating when I haven't tried the recipe yet. Why are you even bothering to write a review? So we do get a lot of off-topic ones too. Or sometimes you have discussions between people not about the recipe or how good the recipe is, but something totally off-topic. So you want to get rid of those as well at some point. So what we're looking into is, are feature selection methods robust across different skewing ratios? And are feature selection methods robust across different domains? So we looked into the cooking data and we looked into the YouTube data with different kinds of skewing ratios and wanted to see what works and what doesn't work. We have information gain as a method. We have odds ratio, binomial separation, and TF-IDF. TF-IDF, it may be the one that needs explaining. That's term frequency times inverse document frequency. So the idea behind that is that you want words that are highly discriminative, and we'll get to the classification part of that. But you want words that occur very frequently in some of the documents, but not in all documents. If they occur across all documents, they're probably meaningless words like and, but, the, for, and whatever, and you don't want those. So we want some that have a high occurrence in hopefully positive reviews, but low occurrence in negative ones, or the other way around. But then they shouldn't be too infrequent. If they only occur in one document, then this person either has a funny spelling, or they use words that nobody else uses, so that they're not really useful in that case either. Okay. With TF-IDF, this was Sun's contribution. She really, really wanted the TF-IDF in there. And I said, this is not something that you normally use for feature selection. And she said, let's try that. So we had to figure out how to actually do that. And what we do is, for each feature, we calculate the TF-IDF with respect to one class. That's my S, sorry about that. And then we normalize two values between 0 and 1, just to make it more reasonable. And then we calculate the TF-IDF with regard to the other class, the negative class, that's not S. And then we obtain the absolute value by the difference between the two. And the larger this value is, the better the ability to distinguish between the two classes. Yeah?
So I'm assuming you're doing this on a training set where you already know the ground truth of what is good and what
no,
is
this
bad.
is totally independent. This is just, so yes, we know what positive and what negative reviews are, yes.
Right. So the yes and the yes. So you have that on a training set, and then you may be using that on a different set.
Yeah, exactly. So we do that on a training set, and then we test it.
So here, your features, are they selected words, or what are your features here?
Yes, there are words. Well, it depends on the setting. We'll get to that. So we'll get to that here. For the Epicurious data set, we've scraped about 10,000 recipes and reviews. And the class in that case is the overall rating per recipe. We cut that down so you can give half forks on Epicurious, or they display half forks. We normalized that to full forks. So if you have 2.5 forks, that was counted as 2 forks. The reason for that being we have a lot of 3 and 4 fork ratings, but we don't have a lot of 2 fork ratings and 1 fork ratings. We excluded reviews that did not have any reviews. Sorry, we excluded recipes without reviews, and we excluded reviews that did not have any rating. If you just leave a review and don't give us a fork, then it's basically not really meaningful for us. And then we had the problem that some of the recipes had a lot of different reviews, and some of them only had very few reviews. So we decided we don't want to bias the classifier towards the ones that have more reviews, because you just get more data. So we cut down everything that had more than 10 reviews down to 10 reviews, and they were randomly sampled. We did remove words occurring less than 4 times on the basis that if they're so infrequent, they're not really good predictors in unseen cases. So they don't generalize well. And we did stemming, and up to this day, I'm not sure if that was a good idea. So stemming means you want to reduce all the word forms to a base form. So if you have, we don't really care whether it's buy, buys, buying, bought. We want to have all of those reduced to the same base form. Well, this is a difficult process, so instead what we do is we just chop off the ending. That's called stemming. And we use the port stemmer for that. For the YouTube data set, we had about 3,000 comedy videos. Turned out by looking at the videos, so these were self-labeled by the people uploading the videos as comedy. Turned out that you have comedies in there where there's a train passing through. Haha, very funny, sorry. But they were labeled as comedy, so we took them. And you have to overall user rating. So this is a scale from 1 to 5. We removed videos, again, with less than 5 comments because there was just not enough data. And we discarded videos with non-English comments. It's surprising how many of those only have non-English comments. And we did normalization, so it turns out that when people write reviews, especially on YouTube, not so much on the Epicurious page, they have very creative spelling. So you get about 10 different variants of cute. And some of them are intended, like you get cute. Some of them are not intended. So I've seen C-U-E-T, for example, for cute. We wanted to normalize all those just to reduce the amount of different words that we had. And we wanted to identify repeated patterns. So if you have cute, that actually has a lot of sentiment in there. Or if you have L-O-L-O-L-O-L-O-L, and so on and so forth, it tends to be about that long. You want to cut it down to LOL, but you want to keep the information that it was repeated a lot of times, because that gives you sentiment. Or if you have, I don't know, 5 exclamation marks, that's sentiment. So you want to keep that information as well. If you look at the skewing ratios, on the Epicurious data set, the most extreme skewing was 1 to 8. So we had only a few negative cases, and negative cases here are ratings of 1 and 2, and we had a lot of positive cases with ratings 3 and 4. And we cut that down. There was a reason why we came up with this funny ratio. Don't ask me which that one was. That was a long time ago. And we went down to 1 to 1. And in the YouTube case, the skewing was even more extreme. It was 1 to 10. And we tried to cut it down to the same ratios as the Epicurious data. We used SVM Lite as a classifier, so support vector machines. And we actually used an old version of support vector machine of SVM Lite. I think it was version 1.1. At the moment, they are at 2 point something. Turns out that the 2 point something classifier works less well on skewed data than the old version does. I don't know what they did to that. We actually wrote to them and asked if they had any explanation for that. We never got a reply. So for Epicurious, we had about more than 10,000 features. So these were individual words in this case. And we did a step size of somewhere between, we started with 500 words and then went up 1,000, 1,500, and so on and so forth. For YouTube, we had overall 23,000 features. We actually stopped adding features at around 15,000 because it took way too long to run the experiments. That was one thing. You will also see that we didn't gain a lot more information at the higher end of the features. Here are the results. So I don't think you can read that, but the red part is information gain. The yellow line is binomial separation. Then the green one is odds ratio. And then the bluish ones are the two versions of TF-IDF. And we have a baseline in here, which is the purple one with the squares. What we see for Epicurious, so these are the different skewing ratios. If we look at 1-to-1, we actually, by doing feature selection, we gain a lot. But only if we keep the number of features that we add or that we use fairly low. So if we have about 2,000 features, we've already gone too far. So at around 1,500 features, 1,500 different words, we get the best results in the classification step afterwards. And here the best one is information gain. And then it levels out. So once you reach a certain number of features, you've learned all that you have, and there's no difference between all the different feature selection methods. If we go to the higher skewing scenarios, so these are the harder ones for the classifier, we see that we have a lot of negative results up here. We don't have a lot of positive ones. And again, at some point it levels out, so at some point when you have a certain number of features, it doesn't matter which feature selection method you choose, they all level out. But at least we're above the baseline. We have some positive ones with TF-IDF1, but then this is hard to tell where you should stop. So TF-IDF1 with only 500 features actually works fairly well. This case is the worst case scenario. So the extreme skewing, it looks like nothing really helps. No matter which features you select and how you select them, it just doesn't help. There's one outlier here. I think that's just random, but we'd have to look into that more. We also looked at the precision for the negative class. So how many of the negative cases that we predicted are actually correct? And the recall of the negative class, so how many of the negative ones that we actually wanted to find did we find? And this is the extreme skewing case. So we can actually see that TF-IDF2, so again TF-IDF worked with only, I think that's 1,000 features. So with 500 features and 1,000 features, both times precision and recall went up. But apart from that, we're just running along the baseline, so nothing really helps.
It seems there's a great variance in performance there.
Yeah.
Just by tweaking the number of features a bit. Is that real? In other words, if you went, for instance, it came down to, I can't see from here, but from the top performance, which is like a 70 something.
Almost 0.8, yeah.
Yeah, and then the next, that one has a certain number of features. I think it's like 500.
This is 1,000 up
1,000,
here.
and then the next point to the right.
The next point is 1,500, and that's at 0.3 maybe.
Yeah. So.
And then we're down at 0.
So does it really fall off that fast, or
these are the negative cases. So these are the very few ones that we actually have, and they're all misclassified as positive cases because this is the majority class. And so this is actually the only way, with TF-IDF, this is the only way of getting at least some of them right. And I mean, the ones, we only predict very few of those, and we predict them with very high accuracy, so the ones that we find are mostly correct up here. But we don't really find all that many. So if you're interested in a highly skewed scenario, if you're interested in finding the negative ones, use TF-IDF and use about 1,000 features. Okay, this is the YouTube data set. That's a little busier. So it turns out that up here we get the best results. So this is one-to-one. So this is the equal case. And we can see that we do get gains, and here's the baseline. If we get to the highly skewed scenario, nothing helps. So I think here they scored one of the negative cases right, and all of them did mostly, and that was it. All the others were wrong. Here again, precision and recall for the negative cases in the YouTube data set. And there's a lot of variation here, so it's really difficult to find out when you have a good setup, when you have a good feature set. But it looks like precision, the one that you find, you normally get right, but your recall is pretty miserable. Okay, so feature selection helps if you have little skewing or no skewing at all. Unfortunately, it does not help if you have extreme skewing. So we're still on the lookout of methods that work better. Yeah.
Was there any reason why you had to fix the two classes instead? Had you used like many comments maybe in the neutral category? So if you have three classes, do you think?
All of these methods are basically based on binary classes. So you choose between two. We're actually planning on extending that to larger classes, but that means adapting the methods or adapting the scenario in which we select them. Which makes the problem even more difficult. For highly imbalanced data sets, we could improve recall a little bit for the minority class, but we couldn't do anything for precision. So the next step that we want to try is, so far we selected words, and there you're walking a fine line between selecting only a few words that are highly predictive of positive versus negative, but then you cannot be guaranteed that they show up in every review. So that if you have too few, you don't generalize well. If you have too many, you generalize well because you will find these words in the reviews, but some of them may not be very predictive. What we want to try next is clustering words together based on their context. And one of the standard methods for doing that at the moment in CL is Brown clustering. So we want to cluster words together and then use the clusters of words instead of using single words. So every time we see one of the words that are clustered together, we count this as one hit for the feature. Ask me again in about a year, and I can tell you how well that works. All right. The next question that we had is how do we deal with the cooking problem? The other question was, can we actually come up with linguistically motivated features that make more sense than just looking randomly at words that happen to be in the reviews? So we used features that we actually came up with ourselves, and we used a sentiment lexicon. So this is a lexicon that has emotion words in there, and I have examples on the next slides. And we wanted to know if that actually works better. Because, I mean, if you're going for sentiment, then emotion words should actually help you. And then the next question was, can we rate the individual reviews in an aggregate, or is it better to rate all the reviews together as one document? The reason why one document may work better is that you just have more data. Individual reviews may be very, very short. If you just have as one word in there, that's hard to deal with. You don't have a lot of information in there.
I think it's very expressive, actually.
Is, yes. But if you have something like no, or but, or so, that's not very expressive. Or okay. Okay can have different meanings, so you don't really know what's going on there. If you go but that also means that you're lumping together a lot of different reviews that express a lot of different opinions. So it turns out that even for the really good reviews, good recipes that were rated very highly, you also have very, very positive and very, very negative reviews in there. So you get a mixed bag, and that can confuse your classifier. Well, if you go to the two-layer approach where you first classify individual reviews, and every review gets a rating, so you don't mix them together, but then you don't have a lot of information. So we didn't really know which architecture worked best, and we want to see what works. Linguistic features. The first one is the percentage of personal pronouns per sentence. Why on earth would that be relevant? It turns out that if people like something, they use a lot of I. I like it. I think this is great. If they hate something, you don't find that I hate it. They try to rationalize why they don't hate it. So sometimes that's too much salt, or this was prepared totally awfully or something. So you're distancing yourself, and that means you're not using I and you. The number of words per sentence. So our hypothesis was that if you hate something, you're being explicit. If you like something, you may just get love it, love it, love it, love it, or something like that. The total number of words in the review, same here. The percentage of passive sentences per review. So again, this is this distancing thing. If you don't like something, then you're trying to be more abstract, and you say, this was not done well, or something like that. You don't say, I don't like it. The number of capitalized characters per sentence. So if you get a lot of love it, love it, love it, love it, there's a lot of, and as all of that is capitalized, that's a lot of sentiment behind that. You can also get hate it, hate it, but I don't think you get that too many times. And then the type token ratio. So how many different words you have in your review. If you have love it, love it, love it, love it, love it, you have exactly 2 different words. That's your type, as opposed to the tokens, which counts every word in a sentence. And that's different from a sentence, I'm not convinced that this is a good recipe, where every word is basically different. The Lexicon, Luke, was published this year. It's a linguistic inquiry and word count lexicon, so it has all these emotion terms. We did a feature selection process on that, and the features selected that were actually supposed to be helpful based on the training data were linguistic processes like negations. So if you have not and don't and something like that in there, that's a good sign. First person plural, we, is a good idea. And exclamation marks kind of makes sense. Psychological processes like love, nice, sweet, hurt, ugly, crying, but maybe because always touch. So if you're wondering about the sexual in here, sorry, I will never learn that. That's in there because it covers the word love. Not necessarily in the sexual sense, but definitely in the sense that I love this recipe. And then we have personal concerns like cook, chat, movie, and words like that that also prove to be important. All right. If we aggregate, we can aggregate in different ways. We just calculate the average over the different reviews, or we can use, again, machine learning, and we tried SVMs and maximum entropy models. The features we used for the aggregation, the machine learning aggregation, were very simple. We counted how many reviews were rated as 1 fork, how many were rated as 2 fork, 3 fork, 4 fork, and then we also used the average length of the review as a feature, because that seems to be fairly predictive. Again, this is fairly similar to the previous setup, except now we don't have positive versus negative. We actually have the 4 different forks readings. And we did a 3-fold cross-validation just to make sure that we don't have any benign data splitting. The baseline for that is using the most frequent rating, which is 3 forks. So for the baseline, we get an accuracy of 56%. If we use information gain with the best number of features, so we went through a whole lot of them, we go up to 62%. And you will see that we gain mostly on the 4-fork rating. So 3 forks and 4 forks are still the majority, and we get a couple of the lower ones right. If we only take the linguistic features, so the lexicon features and the ones that we came up manually, we're down to the baseline. So that means we're always going for the majority class. If we actually add the lexicon features to the information gain features, we gain. Just a tiny little bit. If we use the information gain and the linguistic features, so how many were there? 7 different features. So by adding 7 features, we actually gain the most. I admit it's still not great, but actually we do gain at least something. And adding the lexicon on top of that actually proves to be useless. So it seems that the linguistic features actually have enough information, and the lexicon doesn't give us anything extra in that case. All right. So these were the best results that we got in that setting. Then we looked at the architecture. Should we do it all in once, or should we do it in 2 steps? And we looked at classifying the individual reviews. And what you can see here, if I highlight the best number, we can actually do better. So classifying individual reviews is easier than classifying all the reviews lumped together. But does that translate overall in a higher accuracy? And I know I have a lot of different numbers. So these are the numbers of features we choose by using information gain. And then this is the average, where you just take the average over the reviews. This is maxm and SVMs. And it turns out that maxm continuously worked better than support vector machines in that case. And the best setting we got was 5,000 features, and we went up to 65. This is an overall gain of 2 percentage points. Not impressive, but at least we gained a little bit. So it actually makes sense to classify the individual reviews. And I think we have to put more work into the classification of the individual reviews, because we have a lot of off-topic reviews in there. And if we kick those out, we might actually have better results. So we should aggregate, and we should use a classifier for that. The linguistically features were marginally relevant. I'm not sure if it's worth the trouble to actually insert them or just go with information gain and give whatever you need. As next steps, we want to explore the aspect level sentiment classification and use more informative features. So my heart is into that part, because I always keep giving the example, I don't think this is a good idea. With the don't, it's not negating the thinking. It's not that you're not thinking. It's that you're thinking that this is not a good idea, so it's a bad idea. So it's not good. And you want to have that kind of relationship. And that you only get by having a linguistic analysis and knowing that the don't actually negates the good idea. All right. Extracting meaning, and I'm almost done. So the goal is to convert sentences to a meaning representation in first-order logic, or more closely in some kind of event semantics. And I have an example, I think, on the next slide. In order to do that, we first need an accurate parser. If my syntactic analysis goes wrong, my semantics, my meaning is way off. So I have to do the syntax first. And this is actually a problem. If you use off-the-shelf parsers, and there are a lot around, and if you look into research papers, they have an accuracy of around an F-score of 90, somewhere, or a little higher than that. So that should be really good, right? Yeah, unfortunately, they're really good on the Wall Street Journal. They're not good on anything else. So if you happen to parse something else, and we definitely do, then the parser is not that good. So what we have to do first is make the parser better on domains that it was not trained on. And then we have to develop a conversion to semantics.
So it was good on the Wall Street Journal because it was trained on it?
Yeah.
Okay.
And there's huge differences. Like, let me give you an example. We tried to parse spoken dialogues once in a search and rescue scenario. So a person was going through a scenario, and they were actually rescuing colored boxes. So you had pink boxes and blue boxes and green boxes. And we had a parser that was trained on the Wall Street Journal. The parser, when it encountered the word left, always thought it was a verb. Because what it saw is sentences like, this person left this company, then and then. If you have a search and rescue scenario where somebody is directing somebody else, you have sentences like turn left. This is definitely not a verb. So you want to get this right, and this means adapting the parser. And then the conversion to logic is really difficult, so we wanted to simplify the sentences. We're in the process of trying to publish something there. So I don't have any results for you, so I'm skipping that. But I want to talk a little bit about how to improve my parser. But before we do that, I have an example from the SynCoin dataset. Anyone familiar with that? Yay. It's synthetic counterintelligence data sets. So they're simulating the situation in Baghdad, and they have a lot of different made-up messages that kind of give you a picture of what is happening, and you're trying to figure out what makes sense. So one of the original sentences could be, Quraysh tells various shop owners he is trying to reconnect with al-Buridi. And in simplified, we're taking out the reported speech part and separating that. So for us, this is meta information. This is not really what we have to represent in the semantics. So we're pulling that out, and the rest of the sentence, in that case, is fairly easy, but a lot of times it goes beyond that. And then the semantics would look like, hopefully will look like that and at some point in the future. So the E's are events. So the telling is an event, trying is an event, reconnecting is an event, and so on and so forth. And the rest tells me which people, which entities are involved in these events. As I said, parsing is normally done on the Pentry Bank, which is the Wall Street Journal. You had a question? Okay. And if we do it on anything else, we don't do really all that well. And normally, we don't have any data in the target domain. So if I want to parse my synchron data, I don't have any 50,000 sentences annotated in counterintelligence sentences. So we're trying to learn how to improve the parser if we have annotated data from the Wall Street Journal, and we have data from the target domain, but we don't have it annotated. And we're trying to use an ensemble approach with different parsers. We also tried code training, which gave us about the same result, but was a lot more work, so I'm focusing on the ensemble approach. Oops.
What kind of errors do you get when you do exactly what you described? You just take the Wall Street Journal system and apply it to Syncoin data? What kinds of errors do you get? I mean, it's a left-left thing, I can understand, but is there more different kinds of errors you get?
Yes, you get. So there's a lot of words that the parser doesn't recognize. I mean, geolocations, you don't have that in the Wall Street Journal. All the names that occur there. But then there's also, it's a lot more subtle than that. So there's some of the rules that we use in syntax that are more frequent in one and less frequent in the other. And this is really hard to quantify. And my parser is always going for the high frequent one, so I'm always getting basically the same analysis, which may be correct in the Wall Street Journal, but not correct in the Syncoin data. So the parsers actually look pretty bad. And for a lot of sentences, we didn't get any of the parsers.
Suppose I give you a whole bunch of machine-generated narratives. Instead of Wall Street Journal articles written by human beings, I give you reports written by a machine about financial transactions. So there's more structure to the inputs. Do you end up creating a new kind of parser, or do you just sort of reverse engineer the model that created the machine-generated?
So for us, the easiest approach is that we actually want to have annotated sentences in the target domain.
Yeah.
So we're saying that let's use 3 different parsers, annotate these sentences, and then take the ones where the parsers agree, because for us, that's a sign that this may actually be the correct analysis. And you want to be a little careful there, because if you add the one-word sentences, they're so easy, you don't really want to add them, so you're focusing on longer sentences. And if you only take full sentences, then you don't get very many where the parsers agree. So we also experimented in having only 2 parsers agree, which is a little more risky, and extracting individual rules where the parsers agreed. So in the partial parts of the sentences where the parsers agreed, and try to add that to the training data. We used the Pentry Bank, either half of the training data or the full training data. My test data was the cooperative remote search task where one person was searching in an environment for the colored boxes, and the other person was outside directing the person. And then we didn't have any unlabeled data from that domain. So what we used is something similar, which is the Edinburgh Map Task Corpus, the HCSC corpus, which is a similar task. So there's 2 people sitting there looking at maps that are slightly different, and one person has to tell the other person how to trace a route on the map. And we hope that this was close enough to get us better results. Unfortunately, there were only 27,000 sentences, which is not a lot. It's a lot to parse, so it actually takes a long time, but it's not a lot to select sentences from, I'm afraid. We had 3 different parsers. I won't go into details. If you want to know the differences between those, let me know. Low par was always the one that we used for the final testing, because that is the one that actually allows us to introduce individual rules and not only instead of just full sentences annotated. Skip that. And these are the results. So it turns out, so these are the baselines. And you can see that we're far away from the 90-something F scores that we're used to on the Wall Street Journal. And we see that the Berkeley parser is the best on the full data set, so that needs a lot of training data. The Big Help parser is actually better. And low par is a plain vanilla parser, so that one actually doesn't work all that well. And if we look, if we add sentences where the parsers agree, we don't really get an improvement. So that was a huge disappointment. No matter what you add, we're slightly worse than the actual baselines. But if we do the parser combination and don't insist on the 3 parsers agreeing, but only 2 parsers agreeing, we actually do get an improvement. It's a moderate improvement, but for us parsing people, if we get a 1% improvement, we're good. We're really doing well. So here, the funny thing is that, remember, we're using low par in the end to parse, but we get the best results if we add the sentences where the Berkeley parser and the Big Help parser agreed. That, in both cases, gives us the best results. And we also see that if we have less data to start out with, we actually we have a higher gain. We're making more progress than if we already had a lot of training data. Yep. So basically, adding the sentences on which the 2 parsers agree helps. Adding partial results does not help for parsing. If we improve part-of-speech tagging, it actually does help. So part-of-speech tagging seems to be more robust towards using partial results. And the ensemble with the different parsers and the code training, which only used 2 different parsers, but then they switched sentences around, that actually reached similar performance. It's just code training is a lot more work. And it's interesting to see that the ensemble method adds more target domain sentences, so we add a lot of different sentences, while code training only adds a few, and it's actually, it's running faster. The development time is higher, but it's running faster. So, to conclude, sorry for keeping you so long, we made progress on feature selection, so we know what kind of methods work. For the highly skewed cases, we're still a little clueless of how to improve that. We're hoping that the clustering will actually help. We can predict the underlying opinions in terms of user ratings to a certain degree. And it's a really hard task. We also tried to do that actually from the ingredients. That didn't work all that well. But I think that's because, I mean, you have soups in there, you have desserts in there, and what's good for a soup, like some salt, may not be good for your dessert, and sugar is good in a dessert, but it's not good in a soup. So maybe splitting those up may actually help. We can improve parsers to work on the target domains, and every percent point that you gain there actually helps a lot. We still need to convert to logical form, so we have the first results on simplifying sentences automatically. So far, this was always done by people writing rules saying this has to move there and this has to move there, and then we're done with this phenomenon. We actually want to come up with an automatic method that learns how to do that from text. And then once we have that, we'll start working on the semantics. Thank you.
Any questions?
Yes. So this is about the recipe ratings and in general about ratings.
To talk into the microphone.
Okay. So in my experience, people are not so good at giving numbers to their ratings, but I'm maybe biased. So have you? What?
This is the microphone.
Yeah.
Okay. So I was wondering if you looked into cases where people are saying, if you follow the same reviewer, they might say, things about it, a very different emotional strength about what they're saying, but giving same number as a rating. Do you usually see that, or?
We don't have that information in the Epicurious data because they don't have any information about who made the reviews. We're in the process of collecting data from Yelp. And there you have at least some information about the user, so you can actually see what kind of scale a user uses. Some people have preferences for using the middle ranges, so they would never go for the extremes. Some other people really like the extremes and wouldn't a lot of times use the middle ranges. So yes, this would be important information. Actually, with the YouTube data, we would love to have a lot more information about the users, because what one user finds funny, the other person doesn't. We have a student working on it, an undergrad, who thinks videos are funny that we look at and say, what? That's funny? And she keeps telling us about her brother in high school who thinks this is hilarious, and she thinks it's just plain old. So the more information you have about the users rating that, the better job you can do, really.
The project title was to do with opinions in social networks. And this whole talk, I think, the network playing in it. And I believe, at least for the YouTube, there is an underlying network. Have you thought about how the network of a person has anything to do with some of these?
We've actually been talking about using networks. At this moment, this hasn't come together for us. A lot of times, because the social network people say they only look at connections between people, but they don't really, they're not interested in what's happening between the two people. So they don't care whether the person says, you're the best person in the world, or I hate you. For them, this is just a connection between two people, and they exchange information, and that's all they care about. I think we should actually look at the meaning of that and put that into the network and see. So this is one thing, because that gives you a lot more information to see what the dynamics in the network are. But then also, we're looking at whether we can influence opinions in the network by having somebody either having a very strong opinion or inserting information into the network. And we're working on that currently.
There's a professor here in the computer science department, Emerson Murphy-Hill, who studies the propagation of tool usage through trust developed through social networks. And he had some students over the summer study GitHub in exactly this way. It's like what users in GitHub are trusted by what other users, and that influences how some users uptake tools. And this may be the same kind of thing where they're uptaking sentiment or they're acquiring the same opinion. That might be an interesting thing to look at, is this notion of trust that's being measured and modeled and understood in a quantitative way.
I think in a way we're trying to model that via giving objective information as opposed to having somebody sitting in there who may not be the most trustworthy person in the world, giving that's the same kind of information.
I have several questions.
Yep.
You can ask one or two.
Why not 16?
So, are you using the TF-IDF to classify these reviews or classifying?
To figure out which words are predictive of positive or negative reviews.
Have you tried to use a POS, a parallel speech tagging, to find a specific structure, like you have our adjective?
Yes, we've done both. We included part of speech sequences, so up to trigrams in some of the experiments. And we had a mixture of parts of speech and words where we focused on trigrams that had adjectives. And actually, it doesn't make much of a difference.
Is that because, like, if you are some examples about the review, some people may say something without many adjectives, but their review are definitely negative or positive?
But since we're doing feature selection, a lot of times the feature selection goes for exactly those adjectives. So you don't even have to worry about excluding stop words, for example, because that's something that they actually manage fairly well. Because stop words occur across all the different categories, they're excluded by the feature selection methods automatically. So we don't even have to kick them out before. They never make it on the lists.
Okay, so when you do classification and your input into the SVM is term frequency, inverse document frequency. And
no. We use the term frequency, inverse document frequency to look at all the whole list of words that occur in the reviews and figure out, okay, this one is predictive, this one is always occurring in positive reviews, and this one is always occurring in negative reviews. That means we cut down the list of words to 500 or 1,000 or 1,500 different words that hopefully are predictive of the two different classes, whether it's good or bad, and as well as frequent across recipes. So if a word occurs only in one review, it's not very helpful because the likelihood of it ever showing up in my test data is not that high. And the feature selection actually gives us a list that has both categories filled. And that we use as features for modeling our recipes, and then we classify them.
Okay, so when you have...
I propose that maybe we meet afterwards.
We can take that offline.
Yeah, we'll take it offline. Any other questions? I do have one quick question. So all of this is great, but there is, I think, another component that I don't believe, in fact, I haven't seen anywhere. How do you factor in the cultural component? Because analyzing, even actually English, even from an Englishman versus an American, they express themselves differently in different ways, in different contexts. So how do you factor that in?
Well, Epicurious is an American webpage. So we would assume that most of the users are Americans, which isn't always completely true. So I found actually, when I was looking for the examples, I found one rating which was, this is a great recipe to share with all your friends, but then the rating was 1. So really bad. Turns out this was a German person, I think, doing the reviews. Because
the French are that way too.
In German, 1 is the grade you can get, so this is really positive. And this person did not look at how the scale is defined. But we would assume that we have Americans in there, and ideally we would like to have different subgroups of that, but we don't. So at this moment we can only hope that in the data set that we have a good distribution of people from different geographical areas of the US.
Isn't there, I would think there'd be a lot of work on looking at how people phrase things and classifying them according to where they are. That seems like something that some government would be interested in.
Yes, we can try to distinguish dialects, and we can try to distinguish, so if people speak English or write English, and if they're non-native speakers, we can sometimes tell what their native language is, because they make different kinds of mistakes. So we could classify those, but honestly, with the reviews, they're so short that we may not have enough data to actually be able to.
Well, it depends on what your intent is to.
All right, let's thank our speaker.